first speaker of this afternoon session is Alexis Prévost from the University of Geneva. Title is First Passage Percolation for Random Interlacements.
Thank you very much. Thank you very much to the organizer for the invitation. It's a pleasure to be back in Cambridge. So I'm going to speak about interlacement, but since it's a word that can be sometimes a bit frightening, let me start with just a simple monomorph, okay, to motivate a bit the kind of problem I'm looking at. So let's say you consider the d-dimensional torus of size length n, okay, and I will always assume that d is larger than 3 throughout the talk, so that the work on an infinite volume is transient. And what you do is you run a random walk on your torus, so you start somewhere at random, okay, uniformly, and then you just do some random walk excursion like that, and when you are at the bottom, you come back at the top since you're on the torus, and you just have excursions like that, okay? And there are two problems that I will be interested in. The first one is, problem A is, does the random walk disconnect 0 from the boundary of a ball, dr. Okay, so dr here, this is a ball of size r. You can see it like that. It's a square like that, of size length r, and we'll always assume that r is, let's say, smaller than n over 2 or something like that. So it's a smaller scale typically than n, but you can take it up to scale n. And so, of course, well, if I just keep running my random walk, then at some point it will happen that the random walk disconnect because just I'm on a finite graph, so the random walk will just visit every point. But the question is, at what time does it happen that the random walk disconnects 0 from the boundary of my box? So here, if I stop at this time, so I'm here, clearly I haven't disconnected, right? Let's say the origin is here. But if I keep running my random walk on my torus like that, then maybe at some point, so this hasn't happened yet, okay, now my random walk has disconnected. Okay, so this point, the origin here, there is a blocking surface made by my random walk around the origin. Okay, so the second question, which is related to the first one, is what is the minimum number of points in the random walk that a path from 0 to the boundary needs to cross. So what this means is that, in a sense, you're counting how many blocking interfaces you have. So here, for instance, my random walk is only need to be crossed once, okay, to go from 0 to r. I can, for instance, go through here, and I only need to cross my random walk once. Okay, so how blocking is really my random walk? Is it just at one place, or is it at many places? So, of course, here I did the picture in dimension 2. So it looks like the random walk is easily disconnecting the origin from the box. So I just need to, to draw a circle like that around that the random walk can do with positive probability, and I will just disconnect, right? But in higher dimension, it's much harder for the random walk to disconnect, and you actually need to wait a much longer time, which is proportional to the volume of the box. So the correct time scale will be to look at time which are a multiple u of the volume of the box n to the d. So I will call I n u, which is just a set of points visited by the random walk at time u n to the d. And we will see in a moment why this is important, this parameter u. And I will also denote by vu, which depends on n, which is just the set of points which are not visited by the random walk, so it's a complement of IU in my torus. And then what I can do is I can rephrase simply the question A in the following question. So A is equivalent to is the path from 0 to R in the vacant set, which avoids the random walk. So, to see a bit what is happening in higher dimension, since I'm not good enough to draw it for you, I have some simulations. I can make it. Okay. It should come in a second. Yeah. So what are you looking at here? The black box in the middle is your box of size R, and actually here we'll be looking at a slightly different problem for better visualization, and sometimes I will talk about one problem, sometimes I will talk about the other, depending on what I need, but basically all results that I will mention will hold for both. You could also ask a question of, can you connect a ball of size R to a ball of size 2R? And then you could also ask the question B from that point of view, by just saying how many points do you need to cross to go from BR, how many times do you need to cross the random walk to go from BR to B2R. Okay, so this is this problem that I'm looking at here. So in black, there is my box BR. I think R is like n/4 or something like that. And the color are all the clusters in the vacant set. Okay, so I'm looking, can I go in the vacant set from my black box to a twice bigger box? And each different color is just a different cluster in the vacant set. They play no role in this question, but it's just for visualization purposes. So, if so basically my random walk has run already a very long time. Okay, so it already disconnects. So my vacant set here is very small. And then if I run my random walk backward, which means I make my vacant set bigger, then all my connected components, they get slowly bigger and bigger, and you start to have a good chance to reach the ball of size 2R, and then you arrive at a certain point where, whoops, I've got some more bigger. Okay, let me just start it again. Okay. And you're at a certain point where you reached the ball of size 2R, clearly, even more, and you even want much further. And you still have multiple clusters which had the chance to do it. So right now it was the blue, okay, but you can see that the green will probably soon also reach the ball of size 2R, and indeed it does. But the blue or purple cluster is slowly taking over everything, and it will absorb every other cluster, and it will become basically the traditional supercritical percolation cluster. Okay? So, this is what the picture looks like in 3. And in order to be able to state question B a bit more precisely, I will define the first passage percolation associated to my model. So this means I have a quantity T which depends on U and N, okay, which is the length of the shortest path from 0 to BR, where I only count 1 whenever I hit my random walk. Okay, so this is the indicator function that gamma I is in my random walk. So this is the random walk at time n to the U n to the t. Okay, and the question is how big is T? Please let me know. I don't exactly know how the room is, how well you can see it on the blackboard from the room. So if at some point I write something and you cannot see what I'm writing, please stop me. Okay, so there is a lot of history that I guess a lot of you know about question A. Okay, And I'm not going to be able to write everybody who contributed to that. Let me just say, so there's Benjamini and Schnitzman, and then the main contribution was made by Schnitzman, who introduced random interlacements. Then there's Windisch, Teixeira and Windisch, and they all proved the same thing, but in various level of precision. So Chani and Teixeira is the most precise one. That is that problem A is related, let's say, to the problem of the phase transition, or let's say the percolation, simply percolation for the vacant set of random interlacements. And I will write often RA instead of random interlacement. And question B, in the same way that this is a percolation question B is naturally with the definition of here for those who know, this is the first passage percolation question. So FPP. Also for the vacant set of random interlacements. Okay, so of course here I'm just saying this is the same, but I'm not saying what is random interlacement. So what is random interlacement? Let me do a short introduction to the model. So, well, the first way to define random interlacement is a way that make this intuition logical, is just to say that random interlacements are just a limit as n goes to infinity of the random walk on the torus. So at time un to the d. Okay, and that's why the problems are related. This is an infinite volume version of my problem on the left here. But of course, this doesn't tell you what they are, and there is a direct way to define them due to Schnitzman in infinite volume. And the definition is pretty simple. So what you do is you fix some finite set k, okay, on ZD. D is always larger than 3, as before. And then you start a Poissonian number of trajectory from K. So what this looks like is the following. You have your set K, which is some subset of D. And then, if your Poisson here is larger than 1, okay, you just start a trajectory. And it's actually doubly infinite trajectory. So you have like, this is just a random walk, okay? And you also have a backward path for it. And the backward path will be like a random walk, but conditioned on not coming back to K. Okay, so here, this is the first time, if you want, that your doubly infinite trajectory hits K. And if you have 2, well, they are just independent. This is a Poisson point process, if you want, of trajectories. So I just start the second trajectory like that, and I do that a Poissonian number of times. So this Poissonian number of times, there are 2 parameters in it. There is the parameter u, which corresponds to the time un to the d over there. And there is a second parameter, which is the capacity of the set k. So for those who don't know what the capacity is, this is just a way to measure the size of your set k from the point of view of the random walk. So basically, the more likely it is to hit a set k, the bigger the capacity. So it measures the likelihood of hitting a set. So for instance, if you have a line, which has a smaller capacity than a box, because it's easier for the walk to hit a box than a line. Right. So this is just, okay, now I've somehow only defined my interlacement on my set K, right? I'm not saying what exactly they're doing outside of K, but there is a consistent way of doing that, so that if you take another set, let's say K prime, okay, then the random interlacement on K prime, they are exactly the random interlacement on K, but you need to add a few more trajectory because the capacity of K prime will be bigger, so maybe your Poisson will be bigger if you couple them correctly. And so you might need to add a few trajectory like that that do not hit K, okay? And you do that consistently And if you let k goes to infinity consistently, this is what gives you the random interlacement process on ZD. Okay? So, to come back to the picture above and to compare the two pictures here that I have, what this looks like here is just, if I take my set k here, right, this red part here will be my first trajectory of interlacement. And then my walk, once it is far from k is finite and fixed, does not depend on n. My walk, once it is far from k, it will basically become independent of what happened in k because of mixing. And then the next time it hit k, for instance through here, then it will just be a new trajectory. So these are just exactly the two trajectories that I drew here. Okay, so that's why how the two models are connected. So this is just the local limit of the model on the left. Okay. And so, to make my correspondence above a bit more precise, let me first introduce some notation. So IU, these are all the points which are hit by one of the random walks. So these are just all my red points here on my drawing. Okay, and VU, this is the limit of V and U, so this is just the complement of IU. So these are all the points which are not hit by any of my trajectories. And so, what Schnitzman proved is that there is a phase transition for this model. So there's a critical parameter, U star, such that if U is larger than U star, then VU has almost surely only finite connected component. So this is a phase transition for the vacant set, finite, let's say, cluster, because the interlacement set, this is IU, is always percolating, and because just a random trajectory percolates alone. So the question is, does the complement percolate or not? And so it's above U star, you're subcritical, you have only finite clusters because VU is a decreasing set. Whereas if I look at below U star, and U star is non-trivial, then VU has an infinite cluster. Okay, and how is that related to my problem A? Well, what all these papers here prove in more or less precision is that if U is larger than U star, then the probability to go from R to 2R in the torus, okay, this goes to 0. Why? Because your vacant set has only finite pictures, so this looks like what I was showing you in the very beginning. Okay, you just have very small vacant set, and so you will not. Sorry, it's in the vacant set. You will not be able, in particular, to go from R to 2R. And on the contrary, if you're below U star, then you will be able to do it. So you will go from R to 2R, and you actually go with probability 1. So this is actually not exactly clear at all that this having a finite cluster is exactly corresponding to that, and having an infinite cluster is exactly corresponding to that. So this is, you need to use some strong result actually on your percolation. That is that the phase transition is sharp. Okay, so this requires sharpness of the phase transition. And this was recently proved by Dumini-Copin. Goswami, Rodriguez, Severo, and Teixeira. Okay, so this is a deep result actually. That you can make this connection exactly with the probability to connect, to go from R to 2R. Okay, so nonetheless, this tells me that a good idea to be able to answer question A is to look instead of random interlacement, which is easier because you don't have a limit as n goes to infinity, you just have your infinite volume, okay, and just look at your model in infinite volume and it's fixed. And then to deduce a result for the vacant set from the fact that the vacant set on the torus is the, if you take its limit, then you have the vacant set for the interlacement. Okay. So now, let's turn to problem B. Okay, now that we've understood a bit better problem A, even if I will come back to it later. So problem B, this looks like, as I was saying, the first passage percolation for random interlacement. So let me first tell you some results about first passage percolation for Bernoulli, so that you can make the parallel with what I will going to tell you for random interlacement later. Okay? So FPP for Bernoulli percolation. So you can define very similarly as I did over there. Your first passage percolation TP, this is the shortest path from 0 to BR, where what you're trying to avoid now is not your interlacement set anymore, but this is your complement of your Bernoulli percolation. So BP, here these are like IID Bernoulli on your vertices with parameter okay. So if you compare the two, here I was saying that gamma I is in the interlacement set, which was the same as saying that gamma I is not in the vacant set, right? And so this was this is the first passage percolation for the vacant set, and this is the first passage percolation for Bernoulli. Okay. So the first trivial result is that for P larger than PC, so PC is the critical parameter for Bernoulli, in the same way as U star was here. So the model is reversed, right? Because BP is increasing, whereas VU is decreasing. So P larger than PC corresponds here to U smaller than U star. So you know that you have an infinite connected cluster. And if you have an infinite connected component, then here, along your infinite connected component, you can travel for free. Okay, your indicator function here is just 0, so you travel for free. So the moment you reach the infinite connected component, you can go anywhere at no cost, right? Almost. So this means, in particular, that your first passage percolation is just bounded. Okay, so this is a constant which is random, but it is bounded in R. So the answer is relatively clear. However, what is less clear is what Kesten proved. This was in '86. And he proved the following. So if P is smaller than PC, actually your speed is linear with high probability. So this means that the probability that your first passage percolation distance is smaller than linear, so it's smaller than some constant times R, this will decay exponentially fast, or some other constant. Okay, and C prime is also a constant at dependent P, not explicit. So this means with really high probability, and with exponentially high probability, actually, I will need to cross R time my complement of BP. Okay, because my clusters of BP are very small, so I need to exit them very often, and actually linearly many times. To go from 0 to R. Okay, so maybe two small remarks about this theorem from Kesten. The first one is that this bound up to constant is sharp. And this is easy to see, this is just the FKG inequality. If you know that you fix a path from 0 to R, and you just open all your vertices, this will cost you an exponential in R, okay? And then if you have opened a path, then your first passage percolation is just equal to 0. Okay, so this gives you an easy lower bound and easy exponential lower bound. So this is actually sharp, up to constant. And the question is up to constant, and what are these constants? That's a $1 million question, but that's another question. And the second remark is that actually Kesten proved something a bit stronger than that. He also proved what happened at PC. Okay, and at PC, he shows that actually this does not happen. Okay, that is more precisely that your first pass, the probability that TP is smaller than CR, this goes to 1. Okay, so you're actually sublinear. You're not constant anymore. That's a good question. Are you constant or not? This is equivalent to theta PC equals 0. But at least you're not linear. Okay, so now let's come back to our question for the vacant set of random interlacements. So I will, in the same way that here I had TU, I can also define the same distance but for interlacement, where I just remove my n everywhere, and this is then my first passage percolation for interlacement. And so the theorem is the following. So this is joint work with Sebastian Andres. That we worked on while we were in Cambridge. So it's a pleasure to present it here. And the theorem says the following. So if U is larger than U star, then the probability that your first passage percolation is sublinear, this decays as the following. So the first one looks exactly like the result from Kesten. Okay. So this is if D is larger than 4. And the second one looks a little bit different. This is that this decays as R over log R actually to the 5. And this is if D equals 3. Okay, so in dimension 4, this is optimal for the same reason as before, because you have FKG. So you can show a lower bound which is matching. In dimension 3, however, it is less clear whether this is matching. You can still get an exponential lower bound, but is there some truth to the log, is the question. And the other question, as before, that I need to mention is that C and C prime, no, and I mean everything, and also maybe I should also mention that this is not true for all R. This is all true for R larger than C second. So C prime depends on P, on U, and C second also depends on U. Okay, so this is all non-explicit in how this depends on U. It's just really, you fix U, which is subcritical, as before, and then you have some constants that depend on U in some way that you don't control. Okay, so one other remark is that actually our method to prove that is quite general. And actually in the paper we don't only prove that for random interlacements, but you can also look at first passage percolation for, let's say, the Gaussian phi field or correlated Gaussian field, Ginzburg-Landau, like all these nice, strongly correlated models, they all fit into a general framework to which you can apply, for which our result hold. Okay? But it holds in particular for this particular case of the vacant set for interlacements. And so now I want to address the log question for the dimension 3, and this will be the second theorem. So I mean, okay, this is a publication date, and this is archive, and this is actually a later result, the second one. So similarly, if U is larger than U star, then for all R larger than, let me call it the same, like C second, you have a bond in dimension 3, which is the following. This is exponential minus pi over 3. You have some epsilon dependency, so this constant will depend on epsilon here. And you are, but most importantly, you have the constant, which is square root of u minus square root of u star square, r over log r. So, a few comments. First, I mean this, okay, actually the one above also, they all require sharpness. So they all use this result from Dumil-Copin, Goswami, Rodriguez, so they want to share. Otherwise, you would have it only for u large enough, some over-critical parameter larger than u double star. And the other comment, which is quite surprising, is that, okay, here my constant is explicit. Okay, what matters is not so much the pi over 3, like this is nice, this is to have the pi over 3, but maybe more importantly is that you have the exact dependency on u. Okay, so this is square root of u minus square root of u star square, and so this is related to the correlation length of your model. Okay, so this means this square root of u minus square root of u star to minus 2. I mean, if I could prove this, so this constant here, it's also depending on u, as I mentioned, depends on epsilon and u. If I could prove this for all r larger than the inverse of this, then this would be exactly the correlation length of my model. But this is really an asymptotic result. Right? So really, as r goes to infinity, in a way that I don't control, I have this result, but here I have the correct constant.
So what you have on the left-hand side, you have c times n.
Oh, sorry, this is an r. Thank you.
So is there c missing on the right-hand side?
No, you're correct. Okay, I need to put my things correctly. So let me put it here maybe. So this is like for any epsilon that exists C. So C typically, if you want your epsilon here to go to 0, okay, you need to make C here go to 0. But I mean, if you don't care so much about this constant pi over 3, okay, and you're mainly interested in that, then you can just take C, this is some constant.
C does not depend on you.
C depends on you, yes, yes.
For that last result, you have a matching lower bound.
Yeah, that's what I want to say. So there is matching lower bound. So this is due to Goswami, Rodriguez, and Shutsenko. So it should be out soon. And they prove matching lower bound, so not for problem B, but for problem A. But basically, lower bound for problem A implies lower bound from problem B. Because if you know that you are connected from 0 to R, then you know that your FPP is 0, so it is sublinear. Okay, so if you combine this result with that result, what you get is that the limit is exactly equal to the constant that you have on the right. So if you renormalize it correctly, so you need to renormalize it by this r over log r, right? Which is what you have in your exponential. Then this converges as r goes to infinity to r minus pi over 3 square root of u minus square root of u star.
I'm sorry, can I check again that the little c depends on you?
Yes, because
so I'm just slightly confused because we are trying to have something which is, and you're trying to capture the dependence in U, right?
I mean, I'm trying to capture the dependence in U here. Imagine if C is equal to 0, okay, which would be somehow the easy case, which is already not easy. This is asking problem A. Okay, probability that TU is equal to 0. This is the probability that 0 is connected to BR.
Okay, so the probability that this probability actually does not really depend on C, does it?
Well, it does depend on C in the sense that here I have an epsilon and I need to make C small enough depending on epsilon. So, I mean, well, okay, if you take C, yeah, you're right, there is a limit missing here, I guess. You need to take a T here, something like that, and to take a limit as T goes to 0. Yeah, you're right. Because otherwise you have a 1 plus epsilon left over. Yeah. So it does depend in the sense that if you want the right constant, you need to make C small enough. Okay, but this is only for the upper bound. Of course, I mean, yeah. The other question is, can you make it go until what the truth is, which is the limit of TU R over R, but this is not clear. Right? You have like the time constant as it is the problem, and that's not clear, however, if you can do that. But I mean, okay, if you don't care about the exact pi over 3, just take C is some constant which is fixed depending on U, but not epsilon, and you have a bound which is explicit in U.
Sorry, what happens to the dash 1 plus power 5? I mean, it's qualitative.
What happened to what?
On the log R. So above you have log R to the 5.
Yeah, so this is a better result.
This is the square root of U.
I mean, yeah, so you have two improvements. You have the improvement from log R to the 5 to log R, and you have the improvement that you also get the correct constant in front. So let me now speak about some history for problem A, which is related to that because this result does not come out of nowhere at all. It is linked to a similar result for problem A. So the first one is so a similar bond, not exactly the same but similar. Was proved for problem A, and for, instead of the interlacements, the GFF, by Goswami, Rodriguez, and Severo in 22. So for the probability to go from 0 to R, not for the FPP. And for the GFF. And they actually also have more, so they have the upper and lower bound that and they also include there's a supercritical case. And this is also the case actually in this paper. There is also the supercritical case. And second remark is, okay, so now somehow you have the same kind of bond for problem A, but for the GFF, how is this linked to interlacement? Okay, how do you adapt the proof somehow for interlacement is the first question. And actually, this is using a technique by Schnitzman in 17, and it considered somewhat the same problem as the problem in red here, but in the supercritical. So if you take U smaller than U star, what it proved is that if you look now at the probability of disconnection, okay, that you do not have a path, so typically in the supercritical you will have a path from R to 2R, and here you look at the probability that this does not happen, that is if you want in a sense that your infinite cluster does not hit PR. Okay? And this decays exponentially fast. And the exponential is actually a super exponential, it's R to the d minus 2. And you have an explicit constant, it's explicit, I will just not write it, and you have a square root of star, U star minus square root U squared, so you have the same as over there.
So it's even
This is for all the so its result is true in any dimension, but mine is in dimension 3.
result here, do you have the constant or?
In dimension 4, you mean?
Yeah.
No. No, it's not here, the constant. And it's,
Even there is no dependence in you?
well, that would be the main question, but no. That's a hard question. So it is expected that the dependency in U stays the same, stays like that, until dimension 6. And that after the dimension 6, you will have a different dependency in U, which will be look more like mean field dependency. Actually, no, it should not be this one. It should be this one, but this should be, this 2 is 2 over d minus 2. Yeah, but this is what it should be in higher dimension until dimension 6, and you should not have the log. That's also the other difference. But and you don't, you know you don't.
You don't have to log in anything above where you're at.
Can I what?
You said you don't have to log in where? In dimensional higher?
So dimension higher, yeah, because you have this result that is already exponential.
Yeah.
So but you expect that this is true just without the log here.
What happens at 6?
Then it's not without this constant. We don't know that constant either. But,
And in dimension 6?
in dimension 6, so I guess you need to make it match. It should be a half.
So you can just keep going.
And in dimension 6 and higher, it's a half. Then it stops.
Okay.
Then your mean field and you don't move anymore. Okay, and basically, the idea is that now you combine the technique for the GFF from Goswami, Rodriguez, and Severo, but you use the tools developed for the interlacement from Schnitzman, and this gives you relatively easily this result over there for problem A, and then you need to work more to get problem B, but I'm not going to go into that. For first passage percolation. Okay. Instead, let me mention another result which is quite linked to this one, which is the same result but on a renormalized lattice. Okay, so let's look at my ball of size R here, and I will split it into smaller balls. Of size small r. Okay, and then I define a new variable, x. So xu is equal to 1 if and only if iu intersected with bxr is non-empty. What this means, if I do a drawing, is that if you have your interlacement trajectory here that maybe does something like that, okay, then I say that this point x here, so the point x here will typically be a point on my renormalized lattice, and I will take that, say that this point x, which is so that the ball here is visited by the interlacement, is occupied. So what this means is that the whole ball here I count it as occupied. Okay, and I do the same here and here. So all of this I consider them now as occupied on my renormalized lattice, this one too. And then, so R is smaller than N, I will have a new excursion of my random walk that will come from somewhere. Maybe it comes here and does something like that. Okay, and then goes away. And so this becomes occupied. And then you ask the same question as before if you want. Let's say question A. Can you find a path from 0 to R which avoids now any green cluster, so any cluster on my renormalized lattice? Another way to ask this is there a path from 0 to large R which does not get too close from the interlacement? Okay? So here this is the case, I can go through here, but of course if I just add one more trajectory here that does something like that, then this is not the case anymore, and here I have this connection on my renormalized lattice, but I do not have, of course, this connection on my initial lattice, because on my initial lattice I could just go through there. Okay, so it's easier to disconnect on the renormalized lattice as on the initial lattice. Okay, and so you can define also problem B. So problem B for this is you have some renormalized by R FPP distance. So you take path from 0 to R, but now your path, they are on the renormalized lattice RZD, and you sum your indicator function that x at gamma is equal to 1. Okay, same as before. Before it was x is in the interlacement, and here it's like x is a distance smaller than r, small r, from the interlacement. Okay? And so in particular, you have TU0, this is just TU. So if you look at this problem of the renormalized lattice, you can prove the same kind of result as you have here. The methods will work, basically. And you have to be careful because the parameter U star is obviously different. Now the parameter U star is your parameter, but on your renormalized lattice. Your critical parameter on your renormalized lattice. So it is slightly different, and you might need to prove sharpness for all of that. But what I will look at actually is one particular value of small r, where actually the problem somewhat becomes simpler. And you can prove stronger results. So let's say you look at the renormalized lattice. With a renormalization which is R, which depends on U. So this will be U to the minus 1 over D minus 2. Okay, this is the correct small r to look at with a large enough constant in front. And then you take R larger than, maybe let me give the number C2 times the same thing. So C2 is larger than C1, typically. You want your large scale to be bigger, but they can be both of the same order, of this order U to the minus 1 over D minus 2. So now you need to imagine that U is small. So this is actually a big scale. Contrary to before, where U it was a constant of order U star. And what you can then prove is the following. In dimension 3, okay, your probability at this scale that your FPP is sublinear, you get the same exponential. So exponential minus pi over 3, 1 minus epsilon. But instead of having U minus U star, you now have U. Instead of having square root of U minus square root of U star square, here you have U. In a sense, it's the same as before, but if U star was equal to 0. Okay? And you can actually also prove quite easily matching lower bound. But there is already a big difference compared to the previous result, is that here, I know explicitly when does this start. I just need to make R larger than in dimension 3, U minus 1. Okay, so the moment this starts to kick in, so maybe I should say, since I say it like that, this is for this one, and the tilde is when I ask to have a path like in from R to 2R. Okay. But the moment this exponential kick in, that is the moment that RU is big enough, then you already have this result. So this is, if you want, in a sense, a near critical result. Okay. This is the first main difference with the overall result on the right. And moreover, you also have, not as explicit, but almost as explicit, dimension in results in higher dimension. So in higher dimension, what you can prove is that you decay exponentially fast, okay? But now you know exactly what your constant is. It's maybe a C3, but C3 is now does not depend on U anymore. This is a fixed constant, and now you know that the dependency is U to the power of 1 over d minus 2, and you have the same for the lower part, with maybe another constant, but that does not depend on U anymore. So the result also in higher dimension gets improved, so you don't know exactly what your constants are, but apart from that, you know the dependency on U in your exponential, and this also starts to be true whenever this in your exponential starts to play an important role, that is whenever RU to the 1 over d minus 2 starts to be big. Okay, so it's a much stronger result than the one on the right. Maybe the question is, but why? How does that, like first, why this scale, choice of scale? And here, R, larger R or small r, this is just the number of boxes. And if I want to go here to R, I just visit R over large R over small r boxes. But why small r like that? And the reason is because if I look at my probabilities at my interlacement at small level, like typically is the case here, intersect BR. So this, or does not intersect, this will be of order exponential minus U. So for both of you know interlacement, this will not be surprising. Exponential minus U R to the d minus 2. So if you take small r of this type, then this will be constant. Okay. So each box here with this scale has exactly a constant probability to be open or closed, even when U is really small. Whereas here, of course, you are only subcritical for U larger than U star. But here, if I take my C1 large enough, I can make this probability as close to 1, I mean, this is a complement, so as close to 0 as I want. Okay, so this is the choice of C1, so that actually this probability is really close to 0, so I'm actually really supercritical, and that's what helps me to the proof. Okay, is that clear? Okay, so I have 5 minutes, I guess. 3 minutes, okay. So maybe, so why do I care about this renormalized lattice, apart from the part that that the result is stronger? There are actually some nice applications of this result. So the first one is about the capacity of random walk and the local uniqueness of random interlacement, and this I will speak about it in more detail for those who will be there in the conference in October. And the second consequence that I want to mention is about the correlation length for the GFF on the cable system. So I will not have time to define this now, and Pierre-François is actually going to define it and go into much more details tomorrow, for those of you who don't know it. But let me just mention the results that you can obtain using this first passage percolation for random interlacement result and using isomorphism theorem between interlacements and the Gaussian phi field. So this is joint work with Alexander Prévost and Pierre-François Rodriguez. And what you can show is that let's call tau h0x. This is the probability to have a path from 0 to x in your Gaussian phi field level set. So more precisely, this is the Gaussian phi field level set on the cable system. So what this means, you have a Gaussian field, okay, and you look at all your points where your Gaussian field is larger than h, and you ask, is there a path from 0 to x where my field is larger than h? Okay, and what we prove is that if I look at the ratio of the off-critical and subcritical, more precisely, two-point function with the critical one, then this decays as exponential minus pi over 6. So this is a slightly different constant, but it just comes from the isomorphism. And then you have the same dependency, instead it's h squared, which replaces u in the previous formula. And we had already proved before, like in 2000 and I think it's 23 or so, a matching lower bound. So what we deduce actually from the result above is the upper bound. Okay, and so this means that the correlation length associated to the Gaussian phi field on the cable system is actually equal to h to the minus 2. And this is, as you can guess from your logarithm here, this is in dimension 3. And you also, we also get some nice upper bound in dimension 4. And intuitively, what is happening is just your clusters of your Gaussian phi field on the cable system. The only way for you to go from 0 to x, and x is here, is to have a cluster of your Gaussian phi field on the cable system, if you know about the isomorphism, which avoid the interlacement. Okay? And if your FPP is very large, it will be very hard to avoid your interlacement, because you will get close to the interlacement many times. Because every time you hit a green here, it means you're close to the interlacement. So if you're close to the interlacement many times, it's very hard to avoid the interlacement. And this is what you use to get this bond. So this bond is actually just formulated differently, the same as the one above, in a sense. Plus some other bonds, but which is negligible compared to this one. Thank you.
Well, the questions or comments?
Are you able to say anything about why you get pi over 3 and also that this Gaussian type?
Yeah, so
I guess I understand why you did
the pi over 3 comes from, so I haven't mentioned it too much here, but this all comes from some capacity computation. So the pi over 3 comes from when you look at the capacity of a line of length r. Okay, so the property that is linked to the property that work in this line. And this capacity of a line will behave exactly as r over log r. Okay, and the constant is pi over 3 in front of it. And then, if you want, in a sense, if you want a lower bound, you cannot saying here that I'm trying to have my vacant set along this line, which is open, and this will cost me, because of my definition here of random interlacement, something which is linked to the capacity of that line. Okay, so the capacity of the line comes from this formula here for the interlacement, and this is where the pi over 3 will come from. And this error comes from, so this is really similar to the work, I guess I raised it, but of Schnitzman. And this comes, if you want, it's come from doing a shifting procedure, where here you're subcritical, and you do a shift in your parameter to arrive at a supercritical case, where you know that this is quite likely. And the error that you make by doing this shift will be exactly of this order. That's where it's coming from. But the fact that it's Gaussian, you can associate from the fact that this model is really linked to the Gaussian phi field. And I mean, this exponential minus u capacity, this is just the probability that the Poisson is equal to 0. And this is also where it's coming from. And this is the probability that this Poisson is equal to 0 is exponential minus u times the capacity. And the capacity of a line is r over log r. So this is where it's all coming from, in a sense.
So the shift here is the same as the shift you get in the isomorphism theorem.
Well, yeah. I mean, yeah, this is deduced actually from here, but you could also do it here by doing a shifting procedure, but it would just be more complicated. But probably you could also do it that way. But yeah, you will get the same. I mean, it's not exactly the same. You have some constant difference, but it's the same idea.
One more short question before the break. Yeah.
Okay, so quickly, what does the square root of u minus square root of u star square?
Yeah.
What does it imply in terms of critical exponent, or at least conjecturally?
So this is this should be the correlation norm. So this is nu. Okay, the critical exponent nu. So nu should be 2 over d minus 2 for the vacant set of interlacements. So if you were to prove this for all r instead of this larger than square root of u minus square root of u star to the power 2 over d minus 2 or minus 2 in dimension 3, then this will mean that nu is equal to 2 over d minus 2. So these are this is exactly what we prove here. Here we really prove that for the Gaussian field on the cable system, because this is really true for all r larger than h2 minus 2. Okay, up to constant. That's what it means. It's about the exponent of nu.
Okay, so let's thanks Alexis again.